Heinemann Higher, Chapter 6 on Differentiation, the mixed exercise success at the end, number 20 in the section on optimization. It's just the same as stationary points. But what does it say for the first part here? It'll just be a little bit of algebra. Express p as a function of x. Well, just now p is a function of x and y. Well, here's a connection between x and y. So I could rearrange this just to read y equals and then substitute for the y. So it'll be 100 minus the 2x, dividing everything by 5, 20, and dividing the 2 by 5, 2/5. I can now substitute that into this. So I'll say that. Substitute 1 in 2, or whichever you wanted to name them. That means 1's now going to read x times whatever y is, 20 minus 2/5 of x, but since it's simply in terms of x, I'll now maybe emphasise that by saying p is now just a function of x, which means p of x is going to be 20x minus 2/5 of x squared. And there's the first bit. Right, that's expressed solely in terms of x. Part B says along the lines of find the maximum value of p. Well, it's an optimum value. So I'm going to differentiate it. So p dash x is going to be 20 minus 2 times 2/5, 4/5 of x. And I'll get an optimum value. I'll get an optimum value here if that derivative is ever equal to 0. Because if it isn't, it'll just keep going on forever. So it must take a turn to get an optimum. Right, well that will do because I've got this simple little linear expression here to solve. So I've got 4/5 of x equals 20. So 4 into that goes 20, 25. Goes 5, 25. So something happens at 25. There's an optimum value at 25. They'll just justify the fact that it's a maximum, even though it said it there, by making up a table. Although I could have used the second derivative. I could have used p double dashed of x, which would be the notation for the second derivative, because that's trivial in this case. Differentiate this again, that goes, linear term, I would only have negative 4/5, which is always negative. That second derivative is always negative, which means the gradient has been slowing down and becoming negative, which means I've got a maximum. That tells me I've got a maximum. That would have done on its own, but I've got the table up there, right? So the table would be something happens at 25, something before, something after, like 20 and 30 for instance. That's the value for x. I want to know what's p dash of x. Well, it was 0 there. Well, if I've got 20, that's just going to be minus 16, making that positive. If that's 30, that's going to be 24, takes away 24, it's going to be negative. So it's looking like this. Same as the second derivative told you about the slowing down gradients. So I've got a maximum. So the question said, what's the maximum value of p? So I know that maximum value of p at x equals 25. So p of 25 is going to be put into the expression. I'll use this one. 25 times 20 minus 2/5 of, so it's going to be 25 times, now 2/5 of 25 is going to be 10. 20 take away 10 is 10, which is 250. So the maximum value of p is going to be 250. I'll put that down again. Maximum p of x equals 250, we'll emphasise it, when x equals 25. Now the last part said, state the values of x and y that give this. Right, so p of x is maximum when x is 25, as I already said, and if x is 25, then this says y is equal to 20 minus 2/5 of 25, just did that down here. So know the answer to that, that's 10. So the values are, p is maximum when x is 25 and y is 10.